Okay, so we ended yesterday with just a comparison. I didn't go through the entire math of how you do the more complicated, non-simple dynamics of replacing the sine function with area function. But this was the summary. And what you see here is that the expression is that of an area function, and we know that the area function has one large maximum at z that's smaller than 0, and then it decays faster than exponential. This is the picture I have in mind. There. So this is the maximum of AI. We somehow managed to get rid of BI by choosing the poleward wall as far north or south, again, depending on the hemisphere, as possible. But if it's farther than z of 2, which translates to a certain number in y, then we are home free. This is almost 0, very close to 0. The contribution of this second linearly independent solution is negligible, and therefore we are able to compute the eigenvalues by choosing the equatorward wall here, and we don't care where the poleward wall is. Just can be anywhere it wants, 2 or 5 or 6, I don't care. Anywhere that's north of, say, 2, or north in the northern hemisphere. So that's where we ended yesterday, and we looked, I didn't do much more math than that. I just summarized all of it with these expressions. So you have the eigenfunction goes like AI instead of sine, and the dispersion relation looks like this, where you have basically the k squared and 1 over rd squared repeating themselves in both expressions. And the only difference is in this meridional mode number in the case of area function. It's a mode number because there is an n here that designates the nth zero of AI. And here you have the regular quantization of the wave number that has, because v has to vanish along the two walls that are separated by a distance of L. So as I mentioned, I think I didn't go much into it. I want to continue from here, and I want to continue in two directions. The first one is to look at the condition for the validity of the trapped wave theory. Why is it trapped wave? Because the amplitude is maximal at some point, finite distance from the equatorward wall. So we have in the northern hemisphere a southern wall, and the southern wall, I come from a place where the western wall is the most important, but we are in the GFD, so its southern wall is the end or the beginning of our domain, and we place it in one of the zeros of the area function, so this becomes 0, and then this is the expression we get. Again, it has to be large. The domain, meridional stretch of the domain has to be large enough. And I think that's where we ended. And just to give you numerical calculations of these simple expressions, you see here the ratio between the omega, okay? So the slope of these curves gives you the phase speeds. The slopes give you the phase speeds. And of course, this is just the dispersion relation. Omega is a function of k, or the frequency is a function of k. And remember, we saw the red ones in the first slide. Remember the Rossby waves that have the minimum, and then they become 0 again at k of infinity. And for different values of this alpha, I remind you, was GH, which is normalized with by some number. So the blue is the trapped wave theory, and you see that the slopes are always larger in the trapped wave theory. Sorry, say again? Yeah, go ahead. No. Well, it depends on... When I look at these lines, they are almost straight. So even though I'm saying the slope, you have in mind d omega dk, yes. But since they originate at 0, what I have in mind is omega over k. But in the realm of interest, they're identical. I'm talking about the c as the slope of these curves, and you are right in saying this is both the phase speed and the group velocity, which in this range of k are identical. Here, of course, they're not identical. Right. Correct. Just one mode at a time. So this is, actually it's the, I think n equals 0 mode. But the slope here is about, you can see it covered in distance of 20, about, what is it, over 2 more frequency units. So it's about 2 point something larger than this one. And the same thing will be here if you look at the small k asymptote. So we get waves that we know qualitatively, I'll talk a little bit more about it, trapped near the equator boundary, and they move faster. So number one, what that I want to emphasize is that from a very, very heuristic points of view, it makes sense. Okay? We couldn't have anticipated it, but once we know these two facts, they somehow add up in a way that makes sense to us. Why is that? Because if you think about the dispersion relation for very small k, okay, very large wave number, then you can expect the frequency of the trapped wave to be how should I say it? Wait, I'm thinking about two things at a time, and I want to somehow. Okay, so the waves here move faster. They're trapped near the equator wave boundary, and what we want to see is what happens if I look now at the eigenfunctions. So I don't want to show you plots because you know basically what's going to happen. It's going to be trapped near the equator wave boundary. And if you compare the harmonic looks something like that. It's a sine wave. Okay, it has a number of zero crossing or number here of m pi over L. And maybe you have the theta here if you want. It won't matter to make sure the boundary conditions are satisfied. And it occupies the entire domain. So it lives on the entire domain from one wall to the other. So you have two walls in the channel, and you have to have these two walls. The eigenfunction fills the two walls. If you look at the trapped waves, then they are proportional to AI, which is a function of Z, which is in itself a function of Y. Okay, we had the exact relation beforehand. And there is a parameter that's the mth zero of AI. Okay, it has zero number 0, zero number 1, zero number 2, etc. They're all tabulated. We know their values. They have a certain value. Like think about something like n pi. They're not multiple of a single number, but they're known. Okay, so there's 1 0 here, 1 0 there, etc. And they're trapped in the equator wall. And therefore, they don't actually occupy the domain from a certain distance from the equatorward wall or the south wall. I want to make 3 remarks when it comes to the eigenfunctions, and let me do them one at a time. In both theories, m, the mode number here and wave number here, actually counts the number of zero crossing, or actually determines the number of zero crossing of the eigenfunction, as in any Sturm-Liouville problem or Schrödinger equation problem. Okay? The m just counts the number of zeros of the function itself. And therefore, there is a big difference in the two sets. In harmonic waves, you have to insist that m be larger or equal to 1. M equals 0 is actually not a solution. Why? Because if you put m equals 0 here, then this v becomes a constant. It's independent of y. And therefore, if you want to satisfy the boundary conditions at the wall, it has to be 0. So v has to be 0 everywhere, which is, again, just exactly the Kelvin wave that we discussed. Remember the first, I think we went over them twice. And they become a legitimate solution only if c squared in the governing equations is equal to gh. In other words, we have the phase speed of gravity waves, okay, which is also the group velocity of gravity waves. So m equals 0 is not a solution, even though people use it everywhere. Okay? The m equals 0 infinitely long waves, people use it in oceanography almost because we cannot determine the wave number. So in the harmonic theory, it doesn't make sense to have, it's not a solution of m equals 0. And the other thing is that in the trapped theory, m can equal 0. It can be greater or equal to, because this psi 0 is a finite number. It's minus 2 point, I can't remember the number exactly, I think 2.331 or something. Okay, but it's a tabulated number, perfectly kosher. And again, if you look at the number of zeros, the number of zeros, it goes this way and decays. Intermediate zeros, the number is 0. There are no intermediate. The function doesn't go through 0 in the domain itself. It just vanishes at the boundaries. I think, okay. Just before I go further, just one more comment. I think I made it yesterday, but I want to repeat it. We're talking about the V eigenfunction that arises from the eigenvalue problem, the Schrödinger or Airy function or whatever. The V is identical. It yields 3 phase speeds, 3 C's, but it's exactly the same eigenfunction. The eigenfunction is identical in all waves. Of course, since the C's are different, the phase speeds are different, then Rossby waves will have negative and small, and Poincaré waves or inertial gravity waves will have large positive and negative values of C, and therefore the U and eta functions will depend on C, and they will be different for Rossby and Poincaré waves. But the V eigenfunction is identical, not happen to be the same. It's not as if, miraculously we found the same function. It is indeed the same function. Yeah. Yeah. But insofar as the eigenvalue is concerned, eigenvalue problem is concerned, you have 1 V. You don't have 3 V's. Correct. No, the eigenfunction and eigenvalues are both unique, both eigenfunction and eigenvalue. But the En, if you remember the end of like 3:30 yesterday, each En gives us 3 C's. Wait a minute, it's not threefold. The eigenvalue problem doesn't know about the C's. Now that we solve the eigenvalue problem, I tell you E0 equals 7, okay? You go from this value that you determine from the eigenvalue problem and say, now I go back and I calculate 3 C's according to the formula we had. The eigenvalue problem doesn't know anything about K or C. No? Eigenfunctions? No. Eigenfunctions are solutions of the eigenvalue problem. You don't have your multiple. Here the eigenvalue is not multiple. From each eigenvalue, you can derive 3 C's. we had the cubic relationship between C and E. Okay? E appeared as one of the coefficients in a cubic. So each E that you derive from the eigenvalue problem gives you 3 C's. And we call 2 of them Poincaré if you are French, or inertial gravity if you are American, and Rossby if you are Swedish, and planetary if you are, you can call them any way you want. Okay, so you have 3 values of C for each value of N. It's not multiplicity because the eigenvalue problem doesn't know about C. Maybe I should go back a little bit. I thought you went over it at night. This is the eigenvalue problem. Okay, you have B, never mind what it is, and you have E. And I'm showing you E is a function of B, has a solution. If you want to go to the harmonic theory, you just set this B to 0, equal to 0. If you want to go through the Airy function, then you set this to be our Z and make it. Exactly, precisely. Precisely. Correct. And V is the eigenfunction. Correct. Of course. No, it depends on it. Of course it depends on it. But once you get E for a certain B, B doesn't know anything about K and C. Okay, it knows about the latitude and it knows lots of things, but it doesn't know about K and C. It doesn't know about the waves. Correct. But the Airy function will have multiple zeros. And therefore, a solution of the problem with the boundary conditions will be, you will have many functions that satisfy it. Correct. As in the case where this is 0, you can have many modes. But the mode number is what determines the En and Vn, corresponding Vn. But once you have En and Vn, or E star N and Vn, now you can go back and say, okay, now I want to translate it to the shallow water equations. In the shallow water equations, each En gives me 3 C's, and I know what to call them. And each C, I can plug into the relationship between U, eta, and V, and then get the U and eta of each of the 3 wave types. Okay, so I just repeat that the M equals 0 is not actually a solution, even though this is what people use when they try to apply observations to the theory. Okay, so what I would like to note is what I said before, that when you go through the math, you need to have a you need to have a domain that's large enough, or L has to be larger enough for such that it is larger than this expression where B is just that. And I want to work a little bit on that expression. Okay, so we have the dimension of B is 1 over length. Okay, it's the cubic root of RD squared, and here in beta you have 1 over A, radius of Earth. So here you have length cubed, and third root of that is exactly has dimensions of 1 over length. And if you translate it to the expression for L, you get an expression that says something like, not something exactly, L over A, the Earth's radius, is being some numerical factor. Okay, it's maybe 2 and psi and etc. times RD over A to the power 2/3. And you see where it comes from. This is 2/3 in R, and if you divide it by A, here you have a 1 over A comes from here, etc. In short, L over A has to be larger than that, than this value, for the trapped wave theory to apply. It doesn't mean that it cannot apply for shorter or for values of L. It means that beyond that, there is no hope for the trapped wave theory, for the harmonic wave theory, I'm sorry. It's only the trapped wave theory that will work. So this brings me to a side issue, which is, it doesn't have a complete solution yet, but it's okay to just say we haven't solved everything yet. And that is, when we look at the beta plane model, okay, we just set out the equation. The question is, what is the relevant length scale on the beta plane? In the parameters or coefficients in the equations, we have two units of length, two values of units length. One of them is the radius of Earth, which arises because we change f on this length scale. Okay, so you have the radius of Earth as one characteristic length. But remember, on the f plane, before you introduced the beta, we also had a combination of parameters that gave us a parameter with units of length, and that is the radius of deformation, or deformation radius, sometimes called Rossby radius of deformation. And this is given by this velocity that we know very well, square root of gh, over f0, which is also a length. So obviously, on the beta plane, the two are working, okay? Both the change of f and the radius of deformation, which we, by the way, encountered in the decay rate of Kelvin waves on the f plane. They will decay exactly on that radius. It typifies many, many behaviors, if you will, on the f plane, which is not the subject here, but this is a very fundamental length scale in the theory of the f plane. Just to give you an example, if you start with a step height, okay, you start at time equals 0 with a dam. You have eta, that's 1 here and 0 here, and the ocean is, say, 200 meters deep. So you have 1 and 0, and you yank the dam. What you'll find out eventually is that the system will develop into what's called geostrophic balance, in which the functions decay exactly on this length scale. This is called geostrophic adjustment. So this is a very fundamental length scale that typifies the dynamics on the f plane. But on the beta plane, we have both of them. So how do they combine? What exactly is the typical length scale on the beta plane? There is no simple answer to this question, but at least from the wave theory, you can learn that L over A has to be something that proportional to 1 over AB, which is RD over A to the power 2/3. Okay? So if you ask me now, what should how should I think of the domain that's relevant to the beta plane? I would say, take the radius of deformation that you know, divided by take this power, and this is the ratio between the acceptable domain scale and the radius of Earth, again, the radius of the sphere. And the interesting thing about this scale is that if you put in numbers, it comes out to be very interesting. Why is it interesting? Because ab initio, when we develop the beta plane approximation, what we say is beta y, or beta L over 2, maximum y, has to be over f0, which equals that, has to be much smaller than 1. Why? Because it's a small correction. Beta y will be a small correction to f0. Now, if you put in the numbers, say we're at 45 degrees, so the cotangent is 1, and L over 2a is, say, less than 1, take any number like 1/2 maybe, okay? Then you get a length scale of about 1,500 kilometers. And indeed, almost Most oceanographers you'll ask will tell you, yeah, something like up until 600 kilometers, the F-plane should suffice. It's okay, it's accurate enough. Between, say, 600 and 2,000 kilometers, maybe the beta plane gives you a very good approximation, and then beyond that, you need the entire sphere, the spherical coordinates. Every practitioner in physical oceanography will give you that kind of numbers, okay? Maybe 500, 600 kilometers for the F-plane. Between that and maybe 2,000 is the beta plane, and then beyond that, the beta plane approximation doesn't work, you need the sphere. But if we put in the numbers on the expression I gave you before, then in the ocean, the radius of deformation is very small. It's about 30 kilometers, okay? 20, 30, 25, 35, it's that order of magnitude. So when you put it in here, you get that L over A has to be smaller than that, which means that L has to be less than 200 kilometers, which is very, very, very tiny, much smaller than people apply to. Again, if you take the L from the wave theory, it doesn't mean that it's the only one. If you now look at the atmosphere, in the atmosphere, the radius of deformation is much larger, say by a factor of maybe 10 compared to the ocean. If you will, the speed of gravity, where the square root of GH, is also about 10 times faster in the atmosphere than in the ocean, in which case you get this number, okay? I don't know why it does this to me. In any event, L has to be about 800 kilometers, still much, much smaller than the 1,500 or maybe over 1,000 kilometers that people ascribe to it or apply the beta plane approximation. Again, it doesn't mean that it's all wrong. It only means that there's much more to the dynamics on the beta plane that is derivable from the geometric approximation of a plane, you know, that you tangential to a sphere. There is more to it. In case of the wave theory, in case then the general rule should be much less than the acceptable number, harmonic theory, of course, it has to be much less than that. The harmonic, remember, the harmonic theory is valid way, way, way below that value of L. So especially for the harmonic wave theory to prevail, not for any general dynamics, it has to be much lower than the 1,500 kilometers. That's usually is the rule of thumb in which people will apply in oceanography and meteorology. Okay, so I want to conclude with the theory and just mention some of the things we covered. So I think I said it earlier today that the eigenfunction of the Schrödinger equation described the amplitude of both Rossby and the inertial gravity waves, okay, and Poincaré waves. It's identical, not for V. If you add the y dependence on F in a systematic and consistent way, then what you get is the trapped waves that are trapped near the equator at boundary in the domain and don't spread like a sine function with several zeros in between the boundaries of the domain. The phase speed is larger in the trapped wave theory, and this is consistent with the lowering of the latitude where you have the amplitude, okay? So if you told someone, look, F is not the center of the channel, it's just closer to the southern boundary. You say, oh, your F is smaller. If F is smaller, I can give you an explanation why the phase speed is larger. I won't go into it, I'm just saying it, okay? There is an argument that goes for infinitely long waves that you have dependence on latitude that's consistent with the fact that you move the amplitude southward or equatorward. And I think that the only good additional thing I can say about this theory is that in principle, the outline that I showed you here, trying to very hard to reach a Schrödinger equation, not necessarily a constant coefficient equation, can also be applied, but it's much, much more complex to the sphere, and I leave that to Friday. Okay, so on a sphere, we can do in principle the same thing, but in principle, with lots of caveats. It's much, much, much more complicated, as you'll see on Friday. So, having solved the analytical part of the theory, the next issue I would like to address is the following. We solved an eigenvalue problem. Okay? We had differential equation, we had two boundary conditions, and we asked ourselves, what is the solution, and somehow managed to get analytic solutions. But what happens if we try and solve the initial value problem? Now, the initial value problem is a much more difficult task, much more difficult than what we've seen now. You cannot just use the decomposition or separation of variables, etc. You have to do much more complete solution. But and of course, the way to go about it is numerical. Just solve the equations numerically. We know how to solve them. And actually today, I think most of our community is engaged in solving these equations using numerical schemes. And what we did in about, 7 years ago, is try to see how the difference between the two wave types and the range of the domain, or the size of the domain, how is it reflected in the initial value problem, okay? So we start with a given state, okay? And integrate the equations. Hopefully we're doing an okay job in integrating the equations. And I'm just reminding you that, again, this is the setup where h is a constant. This is eta, and we add these are the equations that we saw before. And since we're solving it numerically, it is very easy to add here, which I'll do at the end, to add here the nonlinear terms of the acceleration. The nonlinear terms are u dx, u dv dx, and et cetera, et cetera. So we have all the advective terms in the momentum equation that will be added up here. But for now, let's concentrate on the linearized system, the solutions of which we know in terms of the eigenvalue problem. So what we want to do now is look at the differential equations, solve numerically the initial value problem, and then analyze the results to see whether the differences we saw in the analytic solutions can be also affect the initial value problem. So I have to just tell you a little bit about how we solve them. You can do many, many, many types of solutions. Today there are many, I think, available, probably hundreds of models, would you say? Certainly many tens of available platforms for integrating the equations. We chose one of them. I'm not sure it's the best. If you criticize the choice of numerical scheme, I'm the first one to admit that there might be better schemes, but all we do is compare the two, okay? We're not interested in practical applications. We just want to compare the two types of solutions. So even if it's not perfect, it's good enough, okay, for the comparison. So what we chose is the domain that is xy is 6,000 kilometers in the x direction, okay? In the zonal direction, in the parallel direction, and it's L, and L will vary L in the meridional direction, and L can be either 500 kilometers, this is a narrow channel, or 3,500 kilometers, this is what we call a wide channel. The definition of wide and narrow are determined just by these two numbers. One of them is narrower or smaller than the other, and we call it a narrow channel. the exact definition of narrow involves also the radius of deformation. It's not that simple, the dynamical definition. But for our numerical purpose, what we take is a 500, which is a narrow, and 3,500 kilometers for a wide channel, okay? No eyebrows raised. The periodic boundary conditions in X, if you solve it numerically, you have to set the boundary conditions both in X and Y. So the boundary conditions in X, since we used, remember in the analytic solution, we had e to the ikx or sine kx, so we need to have a boundary, periodic boundary conditions, right? The eigenfunction is periodic in X, so we took it to be 2 pi over 6,000, which is about wave number 1, right? Wave number 1 in X. Okay, so it's just periodic. So the function goes, whatever happens at the kilometer 6,001 is identical to what happens at 1, etc., etc. And then at the meridional channels, okay, at L, we set the velocity to vanish there. So this is numerical integration in a domain where the boundary conditions in X are oscillatory or periodic, and one condition in Y are the Dirichlet boundary condition, okay, vanishing of the function. Okay? The numerical, other parameters we chose was that we centered our center of the channel at 35 degrees latitude. This ensures that this doesn't cross the equator, so we don't have a channel that goes beyond the equator. The radius of deformation we chose such that the height, the mean thickness of the fluid, layer of fluid, is 200 meters. So if you translate it to the radius of deformation, the square root of GH over F0, it comes out to be about 500 kilometers. Okay? It's important because definition of narrow and wide are not that simple. According to the value of L I gave you before, right, the boundary at which the trapped wave theory begins to be valid, the number I showed you before, the channel has to be with L larger than 3,700 kilometers. We have a little less than that, but it's very close. It's close enough, okay? So our channel is only 35, but a little less for the trapped wave solution to prevail. So far, so good? Okay. And I think as far as the numerics is concerned, we had a finite difference leapfrog scheme on an Arakawa Sigrid with uniform resolution of delta x delta y equals 10 kilometers. So here we had 600 points, and here we had about 50 or 350 points. We also had the Robert Aislinn averaging with a 0.05. Those of you who understand what it is, it means something. Those of you who don't, just a way, if you ever want to repeat it, the numbers are here. Just a standard way, maybe not the best way. Okay, now what we do is we say, okay, we will initialize, we solve an initial value problem. So what we'll do is we take the analytic expressions I showed you in the beginning, or in the last, like maybe 20 minutes ago for V, derive from it the corresponding expressions for eta and for U, okay? And this will be our initial condition. So we'll initialize the numerical solver with the exact solution of the linearized equation. Now, if the numerical solution is perfect, then what we'll see is just the wave propagating, right? Because we started with the initial value, with the exact initial, the initial conditions are the value. And we take the simulation for 100 days. We integrate it for 100 days, and I don't think I remember what the temporal resolution, probably to satisfy the CFL condition. So it's sufficiently dense that we could do a 100-day simulation on a laptop. Okay, these are the numerical parameters and, if you will, the setup of the numerical problem. We initialize it with the analytic solutions, and we just examine what happens to the solution. Does it really move? Remember, the computer doesn't know anything about C. It only knows the field of U, V, and eta in both cases. It doesn't know that there is C behind it. Somehow it may be able to identify the K, but it doesn't know that it doesn't appear in the equations. It just integrates it. So will we see the solution we came to appreciate until now? So let's start with the narrow channel. So we have a channel that's 500 kilometers wide, and we know the solution. So the analytic solutions are exactly those sine waves, okay? Sine in both y and x. And we ask ourselves, what happens to it? So look at, first of all, here, okay? So what I'm showing you is the beginning. I think this is the eta field, okay? So I'm showing you the field of eta, how the sea surface height looks. Here is the day equals 0. Look at this one. This is the harmonic, okay? So this is the solution for a harmonic wave, and this is what happens when we start with the trapped wave. Okay, so we start with the two wave types. Again, V, U, and eta derived for the harmonics from the harmonic solution, and U, V, and eta derived from the trapped wave solution. And we set it up, time equals 0, and we let it go. And I'm showing you here 4 snapshots, time day 25 up to day 100. Okay? So the initial conditions and day of 100. And what you see is that after 100 days, the harmonic wave simply propagated. And if you can even calculate the speed of propagation by just taking those crests of the wave, okay, these are maxima of the wave. Remember, we started with, this is what their height, and you can see it propagating slowly. You can calculate the phase speed from these numerical solutions, and it matches the solution we got from the analysis. In other words, it's about 10 kilometers per day. So in 100 days, it moves 1,000 kilometers, which is about 1/6 of this whole domain. So in the harmonic theory, in a narrow channel, the harmonic solution is a perfect solution, no question about it. Now, what happens if we put in the trapped wave solution? Again, it's the Airy function type, and what you see here is that the mode is completely destroyed. You have nothing remaining after 100 days that reminds you of the K of 1 and the eta that we saw initially. What happens now if we take the same thing and do it in a wide channel? Okay? So we start with the same initial conditions, just put it in a wide channel. Okay, so it's 3,500 kilometer wide channel. And what you see here is that the harmonic wave is almost lost. At some point, you can maybe see remnants of it, but definitely not continuously. If you look at the trapped wave solution, okay, this is the Airy function type of solution, what you see is that the wave propagates much, much, much faster. Number one, it propagates. Okay, you see, it just propagates westward as we anticipated, again, for Rossby waves. But it propagated much faster. At each 25 days, it actually went across this way. Okay, so it went completely, remember, it's periodic boundary condition. So the solution, this height, went all the way through and came back, and now you see it here. So this is not the speed at which it propagated. The speed at which it propagated is it covered in that 25 days, it covered the full length of the channel plus this difference between the two of them. So you can calculate the speed, and it's about 320 kilometers per day as compared with the 10 kilometers per day that we saw for trapped waves. And indeed, you see that it's actually moving the way it should. It's not perfect. You see, it's a little higher here, but with the resolution and graphics that we use, it works pretty much the way we expect it to be. Okay, so what I'm saying is this really moves, those waves really move fast. Yeah. So the trapped wave move fast as we anticipated in the analytical part. They also move fast in the solution, much faster than the linear wave. So the beauty of numerical solutions is that it's fairly easy to code in the nonlinear terms. Okay? Just add it. You know, since you are computing derivatives numerically, you can compute the derivatives of u dx and dv dy, and et cetera, multiplied by u. It's not that there are no subtleties in there, but insofar as the programming is concerned, it's not a big issue. You can just put in the nonlinear terms into the equations. Now remember, these are everything we did in the analytical part, okay, in the theory of the eigenvalue problem, of course, has to do only with the linear dynamics. So we didn't have nonlinear terms. We don't know what to do, but it's fun. Just go ahead and do it with the nonlinear, do the numerical simulations with the nonlinear terms coded in. Okay? So let's see what happens. So, right, so we do the same thing, again, the same initial condition, the same scheme, the same, everything is the same, except that the nonlinear advective terms are added. So the change, the time derivative is not anymore the partial derivative, but the full time derivative, meaning d dt plus u du dx, et cetera, et cetera. You know what these terms are. I think this is incorrect. It's v, you know what I mean, okay? It's not v dot, it's not exactly v, it's not the, you know what these terms are, okay. Right, everything is in a plane. No. When you live on the beta plane, like in 1,000 pages of Pulaski or Vallis, you don't know that there is a sphere around you or that you're stepping on a sphere and you're about to perhaps lose touch with it. You are on a plane, that's it. And on that plane, f varies linearly with the meridional coordinate. Okay? So up until now, everything has to do with the plane. We don't compare it to the sphere. Okay, so so we do the exact same experiment. I shouldn't say experiment. The same simulation, with the nonlinear equations. So again, n equals 1. The parameters are k is this, n is 1, as I said. Rd is the same as before. Now the amplitude of eta becomes important, so I'm just telling you that it's 1. It was also 1 before, 1 meter. Remember, the mean thickness of the layer was 200 meters. Okay? So whether you do nonlinear or linear, the ratio of eta to h is still 1 in 200, very small. And again, L of 500 kilometers will be narrow, L of 3,500 kilometers will be called wide, as was the case before. Nothing changes. So what we did is we simulated every wave type in its realm of applicability. Okay, so in a narrow channel, the relevant solution, or the correct, or how should I say, the accurate approximate solution, approximate but accurate, was the harmonic solution. So we start with the harmonic solution in a narrow channel. No need to do the trapped wave solution because this even didn't withstand the linear dynamics. In the nonlinear, it's going to get ruined. And so what we see is that somehow the wave, not completely, but certainly loses its typical structure within something like, it depends on the taste or personal attitude, but something like 20 days. It's certainly by day, this is 50, this is not anymore wave number 1, okay, in here. So somewhere around, say, 20, maybe even before that, it's already seriously damaged. And remember that the amplitude is eta, the maximum value of eta is 1 meter in both of them. Now we go to a wide channel, and in a wide channel, of course, we'll simulate the trapped wave solution because this is its realm of applicability. So here is the solution of the trapped wave with the nonlinear terms in a wide channel. So again, the channel is 3,500 kilometers. Everything is the same, but you see that the mode is very, maintains the same structure with simple propagation, even in the nonlinear equation. So it's fully preserved, and the speed of propagation, again, remember that it does, this is not the speed, this line. The speed is, it goes around the channel and comes back. So the speed is like 7,000 kilometers in 25 days, okay, much, much faster. So what I want to do is I think I want to leave you with a question. Why do linear trapped waves solve the nonlinear equations while for the same amplitude, linear harmonic waves don't? Okay, so what we saw is that the linear solution of the trapped waves satisfies, or again, numerically, it's not exact in terms of analysis, but it satisfies the nonlinear equations, but harmonic waves don't. What can be the reason? So when we published the paper, we wrote at the end of the discussion that this needs further examination. So I'll give you 1 minute to think about it, and then I'll give you the examination that's actually not very complicated. But remember, we take linear waves, simulate it non-linearly, it's destroyed, while linearly, it keeps itself. We do the same thing with trapped waves, and somehow it survives the non-linearity. Yeah. No, just a line that I wrote. It's one line that I wrote. It's fairly surprising. It's very clear. This observation is very clear. And the answer, I think, simple, maybe you'll find it to be not so. Okay, so the answer is to look at the phase speeds. I told you that the harmonic phase speed is about, remember, 10 kilometers per day compared to 320, I think, kilometers per day. So the phase speed of trapped Rossby waves is about 32 times higher than that of harmonic waves. So trapped waves move fast, very, very fast. C is large. And if you now go to the equations and you say, let's see what happens when we compare the ddt with those terms, those advective terms, then the v dot del goes like maybe IKU, where u is the velocity, and ddt goes like minus IKC, so forget about I, forget about K, forget about minus. So the ratio between the advective terms and the explicit term is about u over c, the mean velocity over the phase speed of the waves. And since the waves in trapped waves c is so much larger, like 32 times larger, then this is very tiny correction for fast waves, whereas for the harmonic waves that move slowly, c is not so large, it's small. Therefore, this ratio is order 1, maybe half, or it's not destroyed right away. But since this is very small, it means, since this ratio is much closer to 1, it means that the advective terms are of the same order, okay? I'm not talking about the factor of 3 as this term, and therefore they affect the solution. The nonlinearity becomes important. Okay, so it took us some scratches over the head. Okay, I think just to recapitulate what I told you today, for the most part, what we see in the numerical simulation is what we saw in the analysis, okay? Not really much, we didn't gain much or didn't contradict anything from the simulation. They basically affirmed the solutions or the conclusions we reached from the analysis. So the harmonic theory is really valid for narrow channels. Allow me now to, maybe it's not order RD, but narrow, sufficiently narrow, and leave it at that. What exactly is sufficient? And the wave theory gives a length scale, a very interesting length scale that is RD over A, and we saw the numbers. The numbers are something like maybe 200 kilometers for the ocean, and again, and about maybe 800 kilometers for the atmosphere, still very low value. Most cases will tell you that 600 kilometers is the range of validity of the F-plane. Now, this length scale comes from wave theory. It doesn't mean that all problems on the beta plane will be characterized by the exact same length scale. So again, the general issue of what determines the length scale on the beta plane, it wasn't really solved. We didn't actually solve it. We just gave maybe a plausible suggestion, okay? That for some problems, I'll be very, very, how should I say, reserved in my statement. For some problems, the relevant scale on the beta plane seems to be going like L over A goes as RD over A to the power 2/3. But maybe in other problems, in other settings, in other circumstances, this is not going to be sufficiently accurate. I think that's what I prepared for today. The next topic, which we'll cover tomorrow, will be now, we did analysis, we did numerical simulations, and we saw the match between them. But perhaps for an oceanographer, both of these are tools. Okay, so an oceanographer, I think maybe Arthur and you are interested in the real ocean. The mathematicians don't really care about the ocean, but still the question is whether the theory has some validity in observations in the ocean. So this is what we'll study next.